very fast, does it? Okay, I'm assuming you can see the first slide.
Yep.
Alo chị Hồng ơi, chị Hồng.
So Vu, I still need your attendance list from your room from last week as well as this week.
Oh, last week I haven't sent you.
Yeah, you didn't send that last week.
Oh, I thought I did. Oh God, really? Sorry. Let me check. Yeah, let me check the mail and I'll send you. Today I
Oh,
don't know where everyone. Maybe they forgot. They come in.
well, John, I don't see some of our regulars on here, but we do
Well,
have a pretty good crew there in Vu's living room.
do you want to wait a couple minutes or start now or
Well,
whatever?
this one's a kind of a short session usually,
Yeah,
so
it's
I
not
don't
too
mind
long.
waiting a little bit.
Yeah, sounds good.
So I have 5 after, so why don't we get going?
Okay, sounds good. Good afternoon, everyone. Welcome to today's session. This session is going to cover safety, and it includes 3 of the sections in the exam pool. One on power circuits and hazards, second one on antenna safety, and the third one on RF hazards. 36 of the 412 questions in the pool relate to safety, and the exam is going to have a total of 3 questions from these topics. As with all of these topics we cover in the classes here, just attending class is not going to be enough to ensure you pass the exam. You should expect to spend at least 8 to 10 hours of outside study for the exam, and we certainly recommend using hamstudy.org in the study mode first, and then into the practice test once you're gone through everything in the study mode, because if you just do the practice tests, you won't see all of the questions unless you do hundreds and hundreds of them. So moving on, let's take a look at the first section on power circuits and hazards. It's going to include several subtopics: hazardous voltages, fuses and circuit breakers, grounding, which will actually appear throughout the 3 sections, electrical code compliance, lightning protection, and battery safety. The second section we will be covering is antenna safety, which will include tower safety and grounding, installing antennas, and antenna supports. It's kind of a generic tower issue. The third topic is RF hazards, and it's going to cover radiation types, radiation exposure, proximity to the antennas and how that affects exposure, recognize safe power levels, and the concept of duty cycle. So we'll start off with power circuits and hazards. And here's a little what not to do.
Wires, and I can't even feel it because the voltage is not high enough. Wow, this is wild. You can see how far this gap is quite wide. Let me measure it for you. Some toothpaste and you're ready to go. It's a very simple and yet effective circuit. Let's turn it on. The skin here is quite sensitive to temperature, and you can tell the temperature quite accurately. This is not the best way, and you might like to try a safer way. Oh, and don't drop the iron on your pants. It's almost finished now. Just need another piece of wire. What did I do?
What the f*** did you do?
I'm fine, thanks.
Idiot.
What? The tip of the gun here simulates a human finger. Always be careful with your tools. That side needs to be connected to ground or negative. It doesn't give me an electrical shock when I do it with my finger. Ow! Ow! But it burns my skin into a charcoal.
All right. Hopefully we're not going to be following that guy's example. All right, here's a picture of a facility. It used to be a computer data center with a battery room and emergency generators in Sacramento, California. The company vacated the building and moved out the computer equipment, but they left the battery backup system in place. And the ventilation for the battery room appeared to be tied to a hydrogen monitoring system, which is a common practice. And the hydrogen sensor was actually alarming when the emergency responders arrived at the scene after the explosion. Apparently the 911 callers said the ones that reported the explosion said they had also been hearing an alarm going off for 3 days. So apparently the alarm was just a local alarm, wasn't, monitored anywhere. Given how slowly batteries generate hydrogen gas, it's likely the batteries were charging for a long period of time with no ventilation. And the detector did its job. It sensed the hydrogen gas buildup, but nothing was done about it. And then eventually there was some ignition source, probably at a grounding strap or who knows what, but something provided that spark that set off a hydrogen gas explosion. And the lesson here is that ventilation is critical with lead acid batteries. You really got to make sure that the ventilation is adequate and that you don't want to ever be charging the batteries if it's not well ventilated. So that's what that picture is all about. So let's talk a little bit about station grounding. For a proper RF ground, you have to use heavy gauge copper, not aluminum, preferably braid or foil and keep the run as short as possible. With grounding, always remember you want to keep short, straight leads. Avoid any bends as much as possible. Short and straight to ground is the best choice. Good ground is going to reduce RFI to the other equipment. It's going to minimize your risk of shock. It's going to reduce electrical interference. You can see here, so this is an example here. They've got a high copper pipe they're using as a ground bus. So each of these pieces of equipment are connected to that bus with a braid or a strap copper. And then that bus is then in turn connected to a ground rod that's in the ground. It should normally be 8 feet long. And that's really long when you think about it. And it's often difficult to drive that into whatever the soil type might be in your area. It could be very difficult. But if you can't get an 8-foot rod in, you might want to use multiple shorter ones. But they need to all be bonded together. And that's another principle, is that we want everything to be at a common ground. So all of your ground wires of any kind should be connected together, should be bonded together so that there's a common ground. You want to use copper, you want to use it short and straight connections to everything. So that's an example of setting up a grounding system for a station. And we're going to talk a lot about grounding today. Lightning arresters. Lightning protection is really important with your station. When you have antennas up in the air, they can act as a lightning rod and attract lightning, especially in areas of the country where you have frequent thunderstorms. Here in Western Washington, we don't experience that so much, but in other parts of the country, it's a really, really big issue. Basically, a lightning arrestor protects the equipment from the power surge you would get from lightning traveling down from the antenna down through the coax. So basically, lightning arresters break that circuit and route that current to the ground. So you want to have it, your grounding, your panel installed near where the feed lines come into the building. You don't want your lightning arresters inside your building, because then you've already got the power surge inside your building. You want to keep it out of the building. And you want to have the shortest, most direct path to ground possible. So you can see here, they've got the lightning arresters connected outside the building. And you can see that's right where the grounding rod presumably is inside that pipe. And you can see where it goes straight down to ground, most direct path possible. So that's some of the concepts for this first section. Some of the definitions throughout this session today are: AC is alternating current, FAA is the Federal Aviation Administration. You should already know FCC is the Federal Communications Commission. HZ for Hertz. PEP is peak envelope power. RF stands for radio frequency. SWR, standing wave ratio. UL is Underwriter's Laboratory. You've probably seen their stickers on a lot of electrical appliances and things around the house. NV for volt. So those are the acronyms you're going to see today. So let's take a look at the first question in this question pool. And I'm going to be going through the questions not in, you can see this is not the first, this is not A01, it's A02, because I'm not going through them in the order they're in the question pool. Instead, I've tried to group them by subtopic so that we're covering all the questions that relate to the one subtopic at the same time. So this is starting with electricity hazards. So what health hazard is presented by electrical current flowing through the body? Well, if you get electricity flowing through your body, it could cause, it's going to heat tissue, can cause burns. It can disrupt the electrical functions of your cells, and it can cause involuntary muscle contractions. So actually, all three of these choices are correct. So which of the following is a safety hazard of 12-volt storage battery? Touching both terminals with hands can cause electrical shock. Yeah, that's possible. That's not the real issue here. Shorting of the terminals can cause burns, fire, or an explosion. That's the key. RF emissions from a nearby transmitter that's a red herring. That has nothing to do with anything. So the answer is shorting terminals can cause burns, fire, or an explosion. What hazard is caused by charging or discharging a battery too quickly? Well, remember when they're charging a battery from our picture of that facility in California, hydrogen gas gets generated, and if it's a closed space, it can create an explosion hazard. So the overheat, the outgassing, the emission of hydrogen gas, it can be caused by charging the battery too quickly. That's the answer to that one. Just think back to that exploded data center. What is the purpose of a fuse in an electric circuit? I think we're all probably fairly familiar with fuses and circuit breakers in our household items. So what does it do? Well, preventing power supply ripple, that's got nothing to do with fusing. To remove power in case of an overload, yes, that's what it does. It doesn't limit the current to prevent shocks. It cuts off the power if a circuit gets overloaded, same as the circuit breakers in your home do. So remove the power in case of an overload. Why should a 5 ampere fuse never be replaced with a 20 ampere fuse? Okay, you got to remember that what this means, what a 5 ampere fuse means is if the current exceeds 5 amps, then that fuse is going to blow and interrupt the circuit. With a 20 amp fuse, the current has to get above 20 amps before the fuse is going to blow. So answer A is the opposite of that. A larger fuse would likely blow because it's rated for a higher circuit. No, exact opposite. The lower rated fuse would blow first. Power supply ripple would greatly increase. That's again nothing to do with anything. And excess current could cause a fire or all of the above. Well, since we've eliminated 2, it can't be all of the above. And again, 20 amp fuse is going to allow more current to flow before it blows. So that excessive current could cause a fire, could melt the wires, could cause a lot of problems. So that's why you don't want to use a higher rated fuse to replace a lower rated fuse. Where should a fuse or circuit breaker be installed in a 120 volt AC power circuit? We want to connect fuses in series because if they're in anything that's in parallel, the current's going to flow, it's going to be split. You want all the current affected by the fuse or circuit breaker. So it's going to be in series. That eliminates C and D. And you want it on the hot conductor only with an AC circuit. Hot conductor only. Oops. What is a good way to guard against electrical shock in your station? use three wire cords, 3-prong plugs for your AC equipment. That is a good practice. Connect all AC powered station equipment to a common safety ground. We showed that in one of the first slides. Install mechanical interlocks in high voltage circuits. What does that mean? Well, if you've got something that has a high voltage circuit in it, you want to have the power cut off if you open up whatever that panel or whatever it's inside of. So all of these choices would be correct answers. All of the above. In the United States, what circuit does black wire insulation indicate in a 3-wire 120-volt cable? You know, I'd say this, I'm just going to have to memorize. The answer is it's the hot wire. It's the hot wire. For DC circuits, which we work with a lot in ham radio, black is the minus or the ground and red is the positive. In an AC circuit, black is the hot wire. What hazard exists in a power supply immediately after turning it off? One of the things that we've talked about I believe in one of the earlier lessons. I'm getting my lessons out of sequence here in my mind. We talked about capacitors and how capacitors store a charge in them and they discharge over time. So if you turn off a power supply, there's still going to be a charge stored in the capacitors. So the problem is if you were to somehow touch that lead, you could get an electrical shock from that. So that's the hazard that exists immediately after turning something off. There would still be charge stored in filter capacitors. So now there's one question in this pool about safety and test equipment. So the odds of getting this are fairly slim, but which of the following precautions should be taken when measuring high voltages with a voltmeter? The answer to this is really the most common sense answer. Ensure that the voltmeter and leads are rated for the use at the voltages you're going to measure. Just make sure that the voltmeter and its leads are the proper ones for the voltages you're going to measure. That is the correct answer. The impedance, that doesn't relate to anything on here. Ensure this it's not grounded. The circuit is grounded through the voltmeter. You're not going to ground a circuit through your voltmeter. And frequency, you're not setting frequencies on a voltmeter. So B is your answer. The last two questions in this section relate to hazards with antennas and feed lines, and they tie into the first questions in the next section we're going to cover. So this first one is, where should a lightning arrestor be installed in a coaxial feed line? Talked about that at the beginning. It's going to be on a grounded panel near where the feed lines enter the building. At the output of the transceiver, it's already in the building, too late at that point. You don't want it at the antenna feed point because then the entire coax feed point is where the coax goes into the antenna. So the whole feed line from the antenna to your house or wherever it's going into is unprotected. And at the AC service panel, that's irrelevant. And so remember, grounded, you want to have your lightning arresters outside the building where it enters the building and at ground. What should be done to all external ground rods or earth connections? Remember I said there are several principles with a ground that you want to have short direct connections and you want to have everything with a common ground connected together. So the answer is you want to bond them together with heavy wire or a conductive strap. You want all your external rods or earth connections to be bonded together. All right. So before we move on to antenna safety, are there any questions about what was covered here? All right, well, we'll move on here to antenna safety. I'm going to talk a little bit about crank-up towers. And as the name indicates, it's the kind of tower you see here in the picture that either hand cranked or power crank of some kind that elevates the sections one at a time for tall towers. Tower work can be very dangerous, obviously working at heights. There's an example of a full body harness, and you can see this guy working on the tower on the right. It's kind of hard to see whether he has an appropriate harness on or not. You can't really tell. That harness should be connected to the tower so he doesn't fall off. And we're going to talk about some of the specifics on tower safety. This is an illustration of ground rods at the base of an antenna. Each leg of a tower should be grounded. Should have ground rods that are, again, 8 feet long. You should have several of them, and they should all be bonded together. And so there's all a common ground. Because you want to think about that tower sticking up there. It's really attractive for lightning. All right. So the first 4 questions in this section are kind of a continuation from the last 2 on the previous section, as I mentioned. So which of the following is a good practice when installing ground wires on a tower for lightning protection? So remember the principles: short, straight, and bonded together. So a drip loop in the ground connection has nothing to do with what we're talking about. Make sure all ground wires bends are right angles. That's the opposite of what we want. We want straight. So the only correct answer is ensure that connections are short and direct. Which is a proper grounding method for a tower? Single 4-foot ground rod driven into the ground no more than 12 inches from the base, a ferrite car RF choke, a connection between the tower base and a cold water pipe, or as I discussed at some length there, separate 8-foot ground rods for each tower leg, bonded to the tower and to each other. Again, that same principle. Everything bonded together, 8-foot rods, short and direct connections. Which of the following is true when installing ground conductors used for lightning protection? Short and direct. Sharp bends must be avoided. Common grounds avoided? No, we want common grounds. It doesn't matter whether the wire is insulated or not. And again, we do not want any bends. Okay. Which of the following establishes grounding requirements for an amateur radio tower? The FCC Part 97, that's the ham radio rules, do not talk about any of this. And the FAA tower lighting regulations have to do with warning lights for aircraft. UL may have some recommended practice, but what applies to us are the local electrical codes. So when we're putting up any kind of a radio tower, antennas or anything like that, we need to comply with whatever the local electrical codes are. All right. The next 3 questions deal with physically working on towers. What's required when climbing an antenna tower? Well, do you think we need to have sufficient training on a safe tower climbing techniques? That's probably a good idea. Do we want to use an appropriate tie-off to the tower? Remember, I was looking on that picture. Is that guy tied off to the tower so he doesn't fall off of it? That would be appropriate. And an approved climbing harness. You're going to be tied off to the tower. You want to be in an improved climbing harness so that it's a safe way to be tied off. So all of these are correct. All of the above. Under what circumstances is it safe to climb a tower without a helper or observer? Cut to the chase on this one. It is never safe to climb without. You always want to have a buddy whenever you're doing this. Doesn't matter whether it's electrical, mechanical work, how high you're going, whatever. You should never work on a tower alone. Which of the following is an important safety rule to remember when using a crank-up tower? Okay, it says tower must never be painted. Don't know what that has to do with safety. Must never be grounded. Well, we know that's the opposite of what's true. So can't be all of the above because the first two are wrong. And clearly the answer is C. This type of tower must not be climbed unless it is retracted or mechanical safety locking devices have been installed. If it's cranked up, if it's extended, and there's not a mechanical locking device, the danger is that it will retract. It will come down on its own. And if you're up on it, that's not a good thing. Not a good thing. All right, so which of the following is an important safety precaution to observe when putting up an antenna tower? Easy way to figure this one out. It says insulate the base of the tower to avoid lightning strikes. You know that you don't want a tower insulated, you want it grounded, so that can't be right, which means all of the above can't be right. And wearing a ground strap to your wrist has really nothing to do with this. So you want to look for and stay clear of any overhead electrical wires. You don't want to hit your tower touching electrical wires. The rest of these questions are going to talk about tower and antenna placement. So what is the purpose of a safety wire through a turnbuckle used to tension guy lines? Well, the best way to do this is, let me just give you the answer and show you an example. It is to prevent the loosening of the turnbuckle from vibration. You can see a turnbuckle here, got the guy wire, and there's a hole. Let me bring you can see here, there's this hole that the safety wire goes through to prevent this side and this side from untwisting from each other. So that's the answer. The safety wire is to prevent the loosening of the turnbuckle from vibration. What is the minimum safe distance from a power line to allow when installing an antenna? Again, let's cut to the chase with the answer. These formulas and things don't really pertain. Basically, the answer is you want to be far enough from the power line. So if that antenna falls, no part of it can come any closer than 10 feet to the power wires. So you got to figure out how tall is your antenna, what's the distance, what's the height of the power wires, all of that. Bottom line is, if it falls, you don't want it any closer than 10 feet to the power lines. Why should you avoid attaching an antenna to a utility pole? We're not worried about 60 hertz radiations on your feed line. And the issue isn't whether or not it's going to work properly because of induced voltages. The big problem is the antenna could contact high voltage power lines because that's what's on a utility pole. So that's the answer. The other part of this is it's also illegal to do that. And a power company finds out about it, they're going to remove it and send you a bill. So it's another good reason not to attach it to a utility pole. Okay, we're moving into our third and final section on RF hazard. Are there any questions about this, what we've covered so far, before we move into this? A lot of those ones in that last section are a little bit common sense, but all righty. Well, let's move ahead with RF hazards. So we're talking about RF radiation. We're talking about non-ionizing radiation. What do we mean? Well, unlike ionizing radiation, which are like X-rays, gamma rays, that sort of thing, RF radiation doesn't have enough energy to cause actual chemical changes in the cells or damage the DNA. However, RF radiation can cause heating of the tissues and can cause burns, RF burns. When the guy in that video was touching that coil that was generating sparks to his finger, he says, well, I'm not getting electrocuted here, but I'm getting an RF burn. Well, that's what we're talking about. You can get a burn from RF radiation. So we're in that non-ionizing range. So the FCC requires stations to evaluate their RF emissions and determine if they're exceeding certain power levels. They have to take certain precautions to protect not only the station operator, but just the general public from being overexposed to RF energy. Again, it's non-ionizing radiation, but it can cause heating of tissue, and that is a health hazard. Notice that the power levels that are listed here depend on the frequency or the wavelength. So we look at it by wavelength bands, and you'll see that the threshold power limit above which the FCC requires you to take certain actions is lower at very certain frequencies. And you can see they're highlighted in yellow there. The power levels are affected. The power levels are different because the body is affected at differently at different frequencies. The body absorbs the certain frequencies of RF radiation more easily than it does others. They refer to it as the specific absorption rate, or SAR, and you can see the highlighted in yellow. It's 10 meter and 6 meter to 1.25 meter. So that's our 10 meter and VHF range, which is what we mostly, a lot of us operate on. That has the lowest threshold at only 50 watts. So if something is above, if you're going to be transmitting above 50 watts, you have to take some additional analysis and some potentially precautions. So that's kind of the key. And you can see that that's 6 meter is right in the middle of that. It's 50 megahertz, 6 meter. That's important. There are several methods that you can use to determine whether your station complies with FCC exposure regulations. The FCC OET Bulletin 65 gives you some calculations that you can use to do that. It can be done with computer modeling. It can be done by actual measurement out in the field. There are different methods for determining whether your station complies, and we'll talk a little more about that in a minute. All right. Another concept that's important is duty cycle. And duty cycle, actually, we talk about two different kinds of duty cycle. Duty cycle refers both to the ratio of the transmit time to the total time, or the transmit time versus the receive time. So if you say something is at 50% duty cycle, it means that it's only transmitting 50% of the time and it's off 50% of the time. If it's a 70% duty cycle, it's on 70% of the time and off 30% of the time. So that's one kind of duty cycle. The other kind of duty cycle we talk about is in the mode of operation. How much of the time you have that keyed to transmit is actually at full power. So let's take the example of single sideband voice. Its output, even though you're transmitting, the actual energy being output varies because its amplitude, or the power level, is being modulated for your voice. So it's not 100%. In fact, single sideband voice, the duty cycle of the transmission, of the actual energy being transmitted, is only 20%. FM, whether it's voice or data, because the amplitude is not what's modulated, it's the frequency. So the carrier is constant and it's at constant power. It's 100% duty cycle. So that's the two different uses of duty cycle. And those both enter into whether or not, or what your actual RF output is. Okay. So the FCC averages the RF exposure over time. They look at 10 and 30-minute periods, and these graphs kind of illustrate that. So the vertical axis is the power level, and time is across the horizontal axis. The shaded areas in here represent the actual RF exposure. So with a lower power level, over a longer period of time might equal a higher power level over a shorter period of time. So it's the total exposure that we're looking at. So as power or duty cycle increase, exposure time can be decreased or must be decreased. As the power or duty cycle is decreased, your exposure time can be increased, and yet you'd still have the same exposure level. So your time, field strength, frequency, the specific absorption rate, those are all critical factors that go into this calculation. And again, the body is most sensitive to VHF frequencies. That's 30 to 300 megahertz. Although interestingly, the eyes are sensitive to energy at 1270 megahertz, can cause cataracts, but most of us don't operate on that frequency. Some do, but not most of us don't. All right, so let's take a look at the exam questions. What type of radiation are radio signals? That is non-ionizing. Remember, gamma and alpha radiation are types of ionizing. RF is non-ionizing. How does RF radiation differ from ionizing radiation or radioactivity? RF radiation does not have sufficient energy to cause chemical changes in cells and damage the DNA. That's the definition of the difference between ionizing and non-ionizing. What factors affect the RF exposure of people near an amateur radio station? Oh, we've been talking about power level and frequency, right? VHF have to have a lower power level. Distance from the antenna to the person will obviously affect it as well, because the closer you are, the more it's going to dissipate it over distance. And the radiation pattern of the antenna. If you have a directional antenna that's pushing energy in one direction, wherever that beam is focused is more hazardous than where the nulls are. So all of these choices are correct. All of these would affect RF exposure. Why do exposure limits vary with frequency? Remember, we talked about SAR, specific absorption. And so the answer is that the human body absorbs more RF energy at some frequencies than others, with VHF being the most concerning. What hazard is created by touching an antenna during transmission? RF burn to skin. Remember the guy touched that coil and got an RF burn? RF burn to skin. At which of the following frequencies does maximum permissible exposure have the lowest value? So here they're giving it to you in megahertz. Our chart had it in wavelength. So 3.5 megahertz is the 80-meter band. That was not one that was a major concern. 50 megahertz is the 6-meter band. That is the one we were talking about. 440 is 70 centimeter. That's above the 300 megahertz, obviously, as is the 1296. Remember, it's 30 to 300 megahertz is the range we're concerned about. So the answer is 50 megahertz. Which of the following actions can reduce exposure to RF radiation? Well, if we're talking about exposure to somebody at a particular place, if you move the antenna away from them, that would help. Relocating the transmitter, well, the transmitter is not the source of the energy, it's the antenna. So that wouldn't help. And we're talking about increasing the duty cycle would in fact increase the exposure. So the only correct answer is relocate antennas. How does the allowable power density for RF safety change if duty cycle changes from 100% to 50%? So we're talking about allowable power. So if the duty cycle is cut in half, then that means the power density can be doubled because it's only going to be going half the time, right? So it increases by a factor of 2. Okay. If duty cycle goes down, allowable density goes up and vice versa. Why is duty cycle one of the factors used to determine safe RF radiation exposure? Remember, this is all calculated on an average exposure that people are going to have. And duty cycle affects the average exposure. If it's only on half the time, on the average, it's much less, right? So affects the average exposure. What is the definition of duty cycle during the averaging time for RF exposure? So it talks about difference in power. Well, we're not talking about power, we're talking about transmission times, right? Difference between the PEP and average power. Now, again, we're talking about duty cycle is transmission times. So it's the percentage of time the transmitter is transmitting. It is not the percentage of time that is not transmitting it. So it's transmitting time. If it's transmitting 70% of the time, it is a 70% duty cycle. Percentage of time that a transmitter is transmitting. Which of the following is an acceptable method to determine whether your station complies with the FCC RF exposure regulations? I mentioned this at the beginning here, that there were several methods you could use. You can use calculation based on FCC OET Bulletin 65. You can look up and do some calculations based on that. You can do calculations with computer modeling. You can get some actual measurements. All of these are correct ways of determining it. Most of us are going to use the calculations based on the bulletin. How can you make sure your station stays in compliance with RF safety regulations? Well, informing the FCC of changes isn't going to ensure that you're doing anything to comply. So it can't be that or all of the above. Making sure your antennas have low SWR isn't really going to make any difference on this. You need to reevaluate your station whenever you change something in your station. So if you change the transmitter, the antenna system, anything in the system, then you want to reevaluate to make sure that you haven't made a change that's going to affect RF compliance, exposure compliance. Talked about the Bulletin 65 calculations. If you go to the ARRL website at ARRL.org, there is an exposure calculator on there, and you can use that to do the calculations. All right. Last question in the pool here. Who is responsible for ensuring that no person is exposed to RF energy above the FCC exposure limits? The simple answer is you are, if it's your station. You, the station licensee, are responsible for ensuring that your station does not expose people to excessive RF energy. All right. That is everything in this session. Any questions on anything? All righty. Well, either that or either everything was covered or everyone's asleep or nobody understood anything.